This video is going to conclude our discussion of single number summaries. So recall that we started out with some very detailed descriptive statistics like the histogram and the frequency distribution. Then we moved on to what I call single number summaries, where we try to capture some aspect of a histogram with a single number. Then we talked about various measures of the center. So the mean, the median, the mode, the trimmed mean, these are all measures of, where is the middle of a histogram. Now we're going to move on and cover some additional single number summaries that capture other aspects of a histogram. So another important feature is how dispersed are the values of a histogram. So is everyone the same, or are there big differences across people in the population? So let me show you two histograms. Suppose that these two histograms have the same scale on the x-axis. The histogram on the right is much more dispersed. So notice the peak isn't nearly as high, and the tails are substantially thicker. Whereas in the histogram on the left, the values are mostly concentrated within a fairly small window. So roughly a third of this range cover most of the values, whereas the values are more dispersed on the right. We care about dispersion for at least two reasons. The first reason is kind of a marketing reason. That is that marketing really addresses situations where people have different wants and needs. All right, so if people have different wants and needs, that's the whole idea of market segmentation. Then we can come in and segment that market and meet the needs better for individual groups of customers. If all customers had exactly the same wants and needs, there'd be no reason to segment that market. So we're going to need to be able to characterize how heterogeneous is a market. How dispersed are the wants and needs? The second reason why we care about these measures of dispersion is that these measures of dispersion will enable us to answer a very profound question. So one of the profound questions of the whole course is, if we'd drawn a different sample, would we come to different conclusions? And it turns out that the standard deviation is going to be the key ingredient to answering that question. It's the whole question of sampling distributions and statistical inference, and we're going to need these measures for that chunk of the course. Okay, so there's, just as we had several measures of central tendency, the mean, the median, the mode, there's going to be several measures of dispersion. The thing that these values have in common is that big means heterogeneous, small means homogeneous. So if we look at these histograms at the bottom, I've computed the three measures of dispersion: the standard deviation, the interquartile range, and the range. I'll define them in a second. My point is that the values for the right are larger than the values for the left. The standard deviation on the one left is 7, and the right at 16. Interquartile range 5 versus 12. All right, so big means more dispersed, small means more homogeneous, more concentrated. Now let's cover a couple of these measures of dispersion. Probably the most important is the variance / standard deviation. Now, really, these two things are the same thing but expressed in different units. So it's not like don't think of them as being radically different concepts. Think of them as characterizing the same thing but in different units. Let's start with the variance. The way to think about the variance is that it is the average squared deviation from the mean. So the squared deviation from the mean is just saying, well, how far are these values from the mean? And we want to find the average of those. Here's the formula. Now, I know that these formulas can be intimidating, so I think it's best for us to work a simple example, and I think you'll get the hang of what's going on with the standard deviation. Go to the next slide. Here is a small data set. the total sales in thousands of dollars for 6 stores. We have a population of 6 stores. During some week are 10, 8, 14, and so forth. Compute the mean and the standard deviation. So I've typed them in here. And let's find the mean. So the mean is we add them up you get 12, or 72, and then we've got 6 values, so 72 over 6 is 12. So the typical sales is 12. And if you eyeball it, sure enough, there's some values smaller than 12, some values greater than 12, so that's about right. Now, let's look at what the variance is. Remember what I said the variance was. It's the typical square deviation from the mean. So let's start out by finding the square deviations from the mean. So how far is 10 from the mean? Well, 10 minus 12 squared, so it's 4 squared units from the mean. How far is 8? We'll take 8 minus 12, you get 4. Square it, you get 16. So 8 is 16 square units from the mean. How far is 14? Well, 14 minus 12 squared is 4. So 14 minus 12 is 2, squared is 4. So we have these squared deviations that characterize how far every observation is from the mean. Now, what we're going to do with these squared deviations is average them. So add them up, divide by 6. So the typical squared deviation from the mean is therefore 16.33 whatever. All right, so it's just the average squared deviation from the mean. The problem with the variance is that it's in squared units. Usually we don't want to think in squared units, we would rather think in unsquared units. So to get rid of these squared units, what we do is we compute the square root of it. So the square root of 16.33 is about 4-ish. And that's going to be called the standard deviation. So think of the standard deviation as the typical deviation from the mean, or standard deviation. The variance is the typical squared deviation from the mean. One more thing about the variance and the standard deviation. The population variance is always going to be called sigma squared. We'll use the Greek letter sigma and the exponents, 2 for squared. The standard deviation will always be represented by sigma, or more precisely the population standard deviation. So these are 2 measures of dispersion. Let's talk about a few more. Another measure is called the range. The range is just the maximum minus the minimum. It's not used much. The reason the range is not used very much is because it's horribly sensitive to outliers. So one value can make the range as big as you want, modifying one value. What's used much more often is something called the interquartile range. So the interquartile range is just the range of the quartiles. So take the 3rd quartile minus the 1st quartile. So the way to think about the interquartile range is it's the range of the middle half of the data. So notice that half the data, the middle half of the data, fall between Q3 and Q1. That's the 75th percentile and the 25th percentile. So the interquartile range describes the range of that middle half. So if you have a very homogeneous population, the middle half will have a small range, and a very heterogeneous population will have a big interquartile range. So interquartile range is kind of a cousin of the median in that it's robust to outliers and it's only based on these ranks. It's you have to have over a quarter extreme values to affect the interquartile range. Both the variance and the standard deviation are very sensitive to outliers, as is the range. So that's it for measures of dispersion. Let's talk a little bit about the interpretation of the standard deviation. This is a rule that you should memorize. It's called the empirical rule. The empirical rule says this: if you have a normal distribution, only if you have a normal distribution, then 68% of the distribution falls within one standard deviation of the mean. So if you go from -1 to +1, so within one standard deviation of that mean being 0, you get 68% of the cases. 95% of the distribution will fall within 2 standard deviations in the mean, and 99.7% of the distribution will fall within 3 standard deviations of the mean. So let's just do a simple problem right now. If we go over to the sketch pad, and I'm going to draw a little normal distribution. Let's say that the distribution of some test scores is normally distributed with a mean of 50 and a standard deviation of 10. Now what we can conclude from this is that if we go 1 standard deviation out in either direction, so let's go 10 to the right and 10 to the left, so 10 to the right puts us at 60, 10 to the left puts us at 40. What we can conclude is that 68% of all people who took this test will score between 40 and 60. Now if we go another standard deviation out, so that takes us to 30 on the left, and we'll go another 10 out on the right, which takes us to 70, then 95% of all people who take the test will score between 30 and 70. If you go 1 more standard deviation out, which takes you to 20 and 80, then 99.7% of all people, which is just about everybody, scores between 20 and 80 on this test. So for normal distributions, there's a very nice relationship between area under the curve and standard deviation. So you should memorize this. We're going to be using it throughout this course and the next course.